NASA, meanwhile, has successfully averted a big problem. Its engineers had sent a wrong signal to Voyager 2 and had lost contact for nearly about 10 days.
Engineers sent a wrong signal to Voyager 2, and now the space probe is on its own at a distance of 20 billion kilometers.
Next, NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again. NASA's Voyager 1 has been zooming through space since 1977, but scientists never expected this. The ancient spacecraft, now 14 billion miles from Earth, just did something impossible. It changed direction on its own. Even creepier, right before turning, it started sending weird signals with patterns that scientists are scrambling to explain. NASA is staying quiet, but insiders are freaking out. Is Voyager trying to tell us something? Did it find something out there in the darkness that changed everything we know about space? The unexpected signal. In the pre-dawn hours of a Tuesday in 2023, Dr. Margaret Chen jolted upright in her chair. The 73-year-old engineer had first joined NASA's Voyager mission in 1972 as a fresh-faced graduate student. Now, nearly 5 decades later, she stared at her monitor in disbelief. Voyager 1, the most distant human-made object in existence, was sending back signals it had never been programmed to transmit. The aging spacecraft, now over 14.5 billion miles from Earth, had spent years sending back predictable data about the interstellar medium. Tonight was different. Buried within the routine telemetry was a faint rhythmic pattern. A low-frequency hum with mathematical precision. The signal persisted across multiple transmissions, ruling out random interference. More alarming was that this mysterious hum had appeared just days before Voyager made an unexpected adjustment to its trajectory, a maneuver no one at NASA had commanded. Fluorescent lights hummed overhead as Chen's colleagues gathered around her workstation. The room smelled of coffee and electronics, the same scent that had permeated mission control since the 1970s, though the computers had changed from room-sized machines to sleek monitors. On screen, the anomalous signal pattern pulsed with unsettling regularity. When Voyager 1 launched, Jimmy Carter was president. Star Wars had just premiered in theaters, and the Apple II computer had just been introduced. Now, those signals traveling at light speed took over 21 hours to reach Earth. Enough time for a person to fly halfway around the world. What had Voyager encountered in the void? What could cause a spacecraft designed to maintain its course through the emptiness between stars to alter its path? The mission that began as an exploration of outer planets had evolved into something entirely unexpected, a mystery at the edge of interstellar space that challenged our understanding of the cosmos and perhaps our place within it. As dawn broke over the Jet Propulsion Laboratory in Pasadena, specialists from across disciplines convened in a secure conference room. The questions hanging in the air were profound. Had Voyager 1 encountered something beyond our understanding? Was this a technical glitch in aging systems or the first detection of something revolutionary? The answer would transform our view of interstellar space and possibly of humanity's solitude in the universe. Origins of a grand journey. The story of Voyager began with a rare cosmic alignment. In the early 1970s, NASA astronomers realized that Jupiter, Saturn, Uranus, and Neptune would soon arrange themselves in a configuration that occurs only once every 176 years. This planetary lineup offered an unprecedented opportunity. A spacecraft could visit all 4 outer planets in a single mission, using each planet's gravity as a slingshot to propel itself toward the next destination. Gary Flandreau, a young engineer at JPL, first recognized this possibility while plotting planetary positions on a circular slide rule. His discovery transformed what might have been separate, costly missions into an elegant grand tour of the outer solar system. The Nixon administration initially canceled the ambitious grand tour for budgetary reasons, but a scaled-back version emerged, the Voyager program, consisting of 2 identical spacecraft tasked with exploring Jupiter, Saturn, and potentially beyond. Each Voyager spacecraft resembled a large mechanical insect standing 13 foot tall with a 12T dish antenna serving as its face. A long magnetometer boom extended like an insect's proboscis, keeping sensitive magnetic instruments away from the spacecraft's own electronic interference. The main body housed cameras, spectrometers, and computers with less processing power than a modern digital watch. The entire apparatus weighed 1,820 pounds, about as much as a compact car, and drew its power from 3 radioisotope thermoelectric generators that converted heat from decaying plutonium into music, electricity. The mission's birth was not without controversy. Environmental activists protested the launch of nuclear material into space, while budget watchdogs questioned the expense of sending probes beyond the acknowledged edge of our planetary system. Nevertheless, on August 20th, 1977, Voyager 2 lifted off. From Cape Canaveral atop a Titan II IE Centaur rocket, Voyager 1 followed on September 5th on a faster trajectory that would allow it to reach Jupiter and Saturn before its twin. Mission planners intended the exploration to last about 5 years. Instead, they created humanity's longest-running space mission and our first true interstellar travelers. The engineering challenges were immense. Designing systems that could withstand decades of cosmic radiation, temperatures approaching absolute zero, and the isolation of deep space. Most critically, the spacecraft needed to operate with increasing autonomy, as communication delays stretched from minutes to hours. Before the Voyagers departed, Carl Schahn and a committee of scientists prepared a special payload, the Golden Record, a gold-plated copper disc containing sounds, music, greetings in 55 languages, and 116 images from Earth. Attached to each spacecraft, these records were a message to the cosmos, a time capsule of humanity intended for any intelligence that might someday encounter these lonely travelers from Earth. Planetary revelations. Voyager 1 reached Jupiter in March 1979, beginning a period of discovery that revolutionized planetary science. As it approached the gas giant, anticipation mounted at JPL. The spacecraft's cameras revealed Jupiter with unprecedented clarity, a world of swirling clouds and massive storms. The Great Red Spot, visible from Earth for centuries, resolved into a complex weather system large enough to swallow 3 Earths. Scientists leaned forward in their chairs as each new image built line by line on their monitors, gasping at details never before seen by human eyes. The discoveries came rapidly after that. Voyager 1 revealed that Jupiter's moon Io, which astronomers had expected to be a dead, cratered world like our own moon, was instead alive with volcanic eruptions. Sulfurous plumes rose hundreds of kilometers above its surface, the first active volcanoes ever observed beyond Earth. This finding alone rewrote textbooks and expanded our understanding of geological forces in the solar system. After Jupiter, Voyager 1 continued to Saturn, arriving in November 1980. Here, the spacecraft's cameras and instruments revealed the true complexity of Saturn's ring. Not simple bands as seen from Earth telescopes, but thousands of individual ringlets with intricate structures. The images showed mysterious spokes moving through the rings and braided patterns that defied easy explanation. Scientists described the sensation of seeing these images as similar to standing before a great work of art, both scientifically fascinating and aesthetically stunning. Saturn's largest moon, Titan, proved particularly intriguing. Voyager found it wrapped in a thick, orange-hued atmosphere that hid its surface from view. Spectrometers detected complex organic molecules in this atmosphere, suggesting Titan might host chemical processes similar to those that preceded life on Earth. Though Voyager couldn't see through the haze, it laid groundwork for future missions like Cassini-Huygens, which would later reveal Titan's methane lakes and rivers. The control room during these planetary encounters was a place of controlled excitement. Engineers and scientists hunched over console, the rhythmic clicking of keyboard strokes punctuating hushed discussions. When significant images arrived, cheers erupted, followed by intense debate over unexpected features. The air felt electric with discovery. Outside the facility, global media gathered, and images from these distant worlds appeared on television screens and newspaper front pages worldwide, bringing the wonder of exploration into living rooms across Earth. After completing its primary mission at Saturn, Voyager 1's trajectory carried it northward out of the plane of the ecliptic, the flat plane in which planets orbit the Sun. This path meant it would not encounter any more planets. While Voyager 2 continued on to Uranus and Neptune, for Voyager 1, the planetary exploration phase had ended, but an even more extraordinary journey was just beginning. The voyage into interstellar space, the pale blue dot, and beyond. In February 1990, before Voyager 1's cameras were permanently shut down to conserve power, mission scientist Carl Schon convinced NASA to turn the spacecraft around for one final photographic assignment. From 3.7 billion miles away, Voyager captured a series of images looking back at the planets. In one of these frames appeared a pale blue dot, Earth suspended in a sunbeam, barely visible among the vastness of space. The resulting image became one of the most profound photographs ever taken. Schon later reflected that this tiny pixel, our entire world, illustrated our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. The photograph transformed scientific data into philosophical perspective, showing humanity's place in the cosmos with cards of humbling clarity. After the pale blue dot portrait, mission controllers commanded Voyager 1's cameras to power down permanently. The camera platform had served its purpose. The future journey would be tracked through invisible fields and particles rather than images. This symbolic moment marked the transition from Voyager as planetary explorer to Voyager as interstellar pioneer. The spacecraft's power supply, its radioisotope thermoelectric generator, continued its inevitable decline, producing about 4 watts less electricity each year. Engineers compared it to a flashlight, slowly dimming over decades. Yet they kept finding ways to read by its light. They implemented creative power-saving measures, shutting off heaters and non-essential equipment. Systems designed to operate at comfortable room temperatures now functioned at near-freezing conditions. The spacecraft's resilience surprised even its creators. As Voyager 1 traveled beyond the orbit of Pluto, still classified as a planet when the mission began, its instruments recorded the thinning of the solar wind, the stream of charged particles continuously flowing outward from the Sun. This region, called the outer heliosphere, represented the fading influence of our star. Scientists eagerly analyzed each transmission, watching for signs that Voyager was approaching the boundary where our Sun's domain ends and true interstellar space begins. The data downlink rate had slowed dramatically since the Jupiter and Saturn encounters. Where once Voyager sent 115,000 bits per second of planetary images and measurements, it now transmitted at only 160 bits per second, slower than the earliest home internet modem. Each precious bit of information traveled across billions of miles, captured by 70-meter antennas of NASA's Deep Space Network. When these signals reached Earth, they were so faint they were measured in zeptos, sextillionths of a watt. Yet they carried crucial information about regions of space no human instrument had ever visited. As the 20th century ended and the 21st began, Voyager 1 continued its silent journey outward, measuring particles and fields in increasingly rarefied regions. The scientists and engineers who had launched the mission as young professionals were now approaching retirement. Some had already passed away, yet the spacecraft they had built continued functioning, outliving some of its creators, carrying humanity's presence ever deeper into the cosmos, crossing the boundary. On August 25, 2012, Voyager 1 recorded a sharp increase in cosmic rays alongside a dramatic decrease in solar particles. Simultaneously, the spacecraft's magnetometer detected a substantial shift in magnetic field direction. These changes marked a historic threshold. Voyager 1 had crossed the helop, the boundary where the outward pressure of the solar wind finally yields to the interstellar medium. After 35 years of travel, a human-made object had entered interstellar space. The confirmation came months later after careful analysis. When the announcement was made in September 2013, it represented a milestone in exploration comparable to the first circumnavigation of Earth or the first footsteps on the Moon. Humanity had extended its reach beyond the solar bubble that had contained all human exploration since our species first gazed at the stars. Voyager 1 was now surrounded by material from other stars, particles and fields that originated in distant supernova explosions and stellar winds from across the Milky Way. The density of electrons in this region was about 80 times greater than inside the heliosphere, creating distinct plasma oscillations that Voyager's instruments could detect. These readings provided ground truth for theories that had previously relied only on astronomical observations and mathematical models. The interstellar medium proved different from what many scientists had predicted. The magnetic field was stronger and oriented differently than expected, suggesting complex interactions between our solar bubble and the surrounding galactic environment. Cosmic ray intensity increased dramatically, showing how the heliosphere had been shielding our solar system from these high-energy particles. Each new data point refined models of this boundary region. Knowledge that would be crucial for planning future interstellar missions and understanding how our solar neighborhood interacts with the broader galaxy. For the public, crossing into interstellar space captured imagination in ways that technical measurements could not convey. The boundary was invisible and had no physical marker. Yet it represented a threshold of profound significance. Voyager 1 had left our cosmic neighborhood behind, entering the vast gulf between stars that humans had previously crossed only in science fiction. News outlets worldwide covered the achievement, and social media buzzed with reactions ranging from scientific excitement to philosophical reflection. The spacecraft itself, of course, experienced no dramatic change as it crossed this invisible line. It continued its steady flight at about 38,000 miles per hour, 17 kilometers per second, neither accelerating nor decelerating as it left the sun's domain. On board, its systems continued their careful management of dwindling power resources, prioritizing the instruments that could tell us most about this unexplored region. With each passing day, Voyager 1 added another 1,000,000 miles to the distance between itself and home, pushing the boundaries of exploration and extending humanity's presence ever further into the void. Power in the darkness, the heart of Voyager. One's longevity lies in its power system. Unlike solar P-powered spacecraft that operate near Earth, Voyager relies on 3 radioisotope thermoelectric generators, RTG, from decaying plutonium-238 into electricity. When launched in 1977, these RTGs produced about 470 watts of electricity, enough to power several household light bulbs. By 2023, this had diminished to roughly half that amount, with output decreasing by about 4 watts annually. This steady decline in available power has forced mission controllers to make increasingly difficult decisions about which systems remain active. The process resembles triage in an emergency room, determining which instruments are most valuable for current scientific objectives and which can be sacrificed. In 2011, engineers turned off the heater for Voyager 1's ultraviolet spectrometer, allowing the instrument to operate at -110 degrees Fahrenheit, -79 degrees Celsius, far colder than its design parameters. Remarkably, it continued functioning. Inside JPL's Mission Operations Center, the Voyager team works in a unique environment that spans technological eras. Modern computers and displays sit alongside vintage equipment maintained specifically for communicating with the spacecraft. Some team members weren't yet born when Voyager launched. Others have devoted their entire careers to this single mission. They described the experience as caring for an elderly relative, respecting its limitations while marveling at its resilience. Every 6 months, the spacecraft must perform a roll maneuver to keep its antenna aimed precisely at Earth. This critical operation uses precious hydrazine fuel from thrusters that cannot be replenished. Engineers estimate that enough fuel remains for orientation control until roughly 2040, though power constraints will likely end the mission before fuel depletion becomes critical. Meanwhile, they've implemented clever software updates transmitted across billions of miles that reduce the frequency of required thruster firing. The Deep Space Network, giant radio antennas in California, Spain, and Australia, spends hours each day communicating with Voyager 1. When signals finally arrive after a journey of over 21 hours, they are so faint that they're barely distinguishable from cosmic background noise. Special signal processing techniques extract meaningful data from what appears to be static. The resulting transmission rate is agonizingly slow by modern standards, 160 bits per second, less than 1/20,000th the speed of an average home internet connection. Despite these limitations, Voyager 1 continues providing valuable scientific data. Its cosmic ray detector measures high-energy particles originating from beyond our solar system. Its plasma wave instrument records the electron density of interstellar space. The magnetometer tracks magnetic fields that permeate the space between stars. Together, these instruments create a unique portrait of an environment we cannot study any other way. The realm through which our entire solar system moves as it travels around the galactic center. Calculations suggest Voyager 1 could continue transmitting scientific data until approximately 2025 to 2030, when remaining power will be insufficient to operate both science instruments and communications equipment. At that point, the spacecraft will fall silent, though it will continue its journey indefinitely. A silent ambassador from Earth, traveling among the stars. The first anomaly. 46 years into its mission, long after many original team members had retired or passed away, Voyager 1 began transmitting something unexpected. Buried within routine telemetry was a faint rhythmic signal, a low-frequency hum unlike anything previously recorded by the spacecraft's plasma wave instrument. The sound occupied a narrow frequency band and pulsed with mathematical regularity, rising and falling in consistent intervals. The detection occurred during standard data collection, as Voyager 1 measured the density of the interstellar medium. Engineers first suspected instrument error or interference. After all, hardware designed in the 1970s and operating decades beyond its intended lifespan could develop quirks. They ran diagnostics and compared readings across different systems. The hum persisted, confirmed by multiple receivers in NASA's Deep Space Network. The control room. Atmosphere shifted from routine to alert. Specialists who had monitored Voyager's signals for decades noted that this pattern didn't match known types of cosmic radiation, solar emissions, or instrument noise. Its structured nature, repeating with precise timing, suggested either a previously unknown natural phenomenon or something with deliberate organization. Some team members were reminded of the rhythmic pulses first detected from pulsars in the 1960s, initially labeled LGM, little green men, until their natural explanation was discovered. NASA assembled a specialized analysis team including plasma physicists, radio astronomers, and signal processing experts. They compared the hum against databases of known cosmic sounds, the emissions from pulsars, magnetars, and distant galaxies. Nothing matched. The sound's characteristics didn't align with theoretical models of interstellar phenomena. Its persistence across weeks of observation ruled out transient events like distant supernova or gamma-ray bursts. The aging spacecraft had detected something new, something unanticipated by the scientists who designed its mission nearly half a century earlier. Team members described the experience as similar to hearing an unexpected knock at the door in a house you thought was empty. The sensation was both thrilling and unsettling. Voyager 1, humanity's most distant explorer, had encountered something unknown, the mysterious course change. Shortly after detecting the unexplained hum, analysts noticed something even more puzzling in Voyager 1's telemetry. The spacecraft had slightly altered its orientation. This subtle yet definitive change in trajectory occurred without any command from Earth. Voyager 1's attitude control system showed evidence of thruster firings that mission control had never initiated. Engineers immediately investigated the spacecraft's autonomous correction systems. Perhaps an outdated command sequence programmed decades earlier had finally executed. They examined contingency routines designed to activate if primary systems fail. Nothing in the spacecraft's programming explained the maneuver. The thrusters had fired in a precise pattern, not the random puffs typical of a system malfunction, changing Voyager's orientation by a small but measurable degree. More puzzling was the specific direction of the adjustment. The shift pointed Voyager's now dormant camera platform toward an apparently empty region of space containing no known stars, galaxies, or other celestial objects of significance. It was as if the spacecraft had detected something invisible to Earth's most powerful telescopes and turned to observe it more closely. The timing raised additional concerns. The course adjustment had occurred within days of the first detection of the mysterious hum, suggesting a possible relationship between the two anomalies. Were they independent coincidences or connected aspects of a single phenomenon? The probability of two unrelated malfunctions occurring in such close temporal proximity seemed remote. At JPL's Navigation Center, specialists worked around the clock analyzing trajectory data. The facility smelled of coffee and ozone from electronic equipment running continuously for days. Monitors displayed complex orbital mechanics calculations and historical telemetry comparisons. The team's expressions grew increasingly concerned as each potential explanation was systematically eliminated. The course change, though slight, held steady in subsequent weeks. Voyager 1 maintained its new orientation rather than drifting back to its previous attitude, indicating a permanent adjustment rather than a momentary glitch. This persistence eliminated several potential technical explanations and deepened the mystery. Whatever had caused Voyager to alter its course appeared to represent a lasting change to its journey through interstellar space patterns in the data. As investigation into the hum and course change continued, data analysts identified another anomaly in Voyager 1's transmission. The spacecraft's radio signals contained subtle modulations, variations in timing and frequency that followed recognizable patterns. These weren't simple distortions caused by interstellar medium interference, but appeared to be structured information embedded within the signal itself. When plotted visually, these patterns revealed geometric ratio, symmetrical intervals, and recursive sequences that couldn't reasonably be attributed to random fluctuations or instrument errors. Some sequences appeared to mirror aspects of Voyager's own transmissions, as if something was responding to or mimicking the spacecraft's communications protocol. The patterns repeated with slight variations across multiple transmission sessions, ruling out one-time anomalies. NASA brought in cryptographers and artificial intelligence specialists to analyze these signal modulations. Advanced pattern recognition algorithms searched for matches with known cosmic phenomena, communication protocols, or mathematical sequences. One particularly unsettling discovery came when researchers identified similarities between certain signal patterns and portions of the Arecibo message, humanity's famous radio broadcast aimed at the globular star cluster M13 in 1974. The scientific community split into competing interpretative camps. Some argued for natural explanations. Perhaps Voyager had encountered an unusual plasma formation or magnetic structure that affected its electronics in ways that generated these patterns. Others couldn't dismiss the appearance of design in the signal. The patterns seemed too ordered, too persistent, and too complex to be explained by known natural phenomena. A broader scientific debate unfolded in specialized journals and closed scientific conferences. Theoretical physicists proposed new models of interstellar medium behavior that might explain the observations. SETI researchers cautiously discussed protocols for evaluating potential non-human communication. Skeptics developed comprehensive analyses of how multiple system failures might create the illusion of patented signals. Throughout these discussions, NASA maintained a measured public stance, describing the anomalies as unexplained data patterns requiring further analysis. Behind this careful language lay genuine scientific bewilderment. The patterns defied conventional explanation, yet demanded interpretation. Universities and independent research organizations worldwide joined the investigation, applying diverse analytical approaches to the publicly released portions of Voyager's data. This global scientific effort transformed what had started as an engineering anomaly into a cross-disciplinary scientific phenomenon, engaging researchers from plasma physics, astronomy, mathematics, and communication theory. Whatever Voyager 1 had encountered, its discovery had catalyzed a remarkable convergence of scientific talent focused on one of the greatest mysteries in space exploration history, Voyager's lasting legacy. Whether the anomalies Voyager 1 experienced were natural phenomena, system malfunctions, or something more extraordinary, they represent the final chapter in one of humanity's greatest exploratory achievements. A mission originally designed to study the outer planets for 5 years has endured for over 4.5 decades, transforming our understanding of our solar system and the space beyond its boundaries. The spacecraft's primary mission yielded revolutionary discoveries: active volcanoes on Io, the complexity of Saturn's rings, the unexpected diversity of Jupiter and Saturn's moons. Its extended mission gave us our first direct measurements of the interstellar medium, the environment between stars through which our entire solar system traveled. Even as its power diminishes and its systems age, Voyager 1 continues providing unprecedented data about regions of space we cannot study any other way. Beyond its scientific accomplishments, Voyager has profound cultural significance. The Golden Record represents humanity's most distant and long-lived time capsule, a message that will likely outlast all other human artifacts. The pale blue dot photograph changed how we perceive our place in the cosmos, providing a perspective that transcends national boundaries and reminds us of our common home. Even the spacecraft itself, a technological relic of the 1970s, still functioning in the most extreme environment imaginable, stands as testament to human ingenuity and craft. If the mysterious signals and course changes ultimately find conventional explanations, they will still have driven scientific progress by challenging researchers to develop new analytical methods and theoretical model. If they represent truly novel phenomena, they may lead to fundamental revisions in our understanding of interstellar space. Either outcome advances human knowledge, the core purpose of exploration itself. Voyager 1 will continue its journey long after its power supply fail and communication cease. Without further course corrections, it will pass within 1.66 light-years of the star GSA 445 in approximately 40,000 years. Barring an extremely unlikely collision, it will travel among the stars of our galaxy for billions of years, possibly outlasting Earth itself. Its golden record may one day be the only evidence that humanity ever existed. What did Voyager 1 encounter in the darkness? What caused it to change course? What generated the patterns in its signals? These questions may never find complete answers, yet in asking them, and following this tiny explorer's journey across incomprehensible distances, we participate in the grand human project of reaching beyond our horizons. Voyager reminds us that the universe contains wonders we have yet to comprehend and mysteries we have yet to solve. Thanks for watching another episode. While you are still here, make sure to click the video on your screen for more quality content. Intent is there is to mais better conduct for the nose. It's audio non intent for the duet only content. For misavor admitted in back. Non-thing war come maze candidates to meet the attack of the Jordan taken at Ward Perry v. Diana Hess. All lowless word. Then a bind below London. War to the Zebedes and its veggies, which it is assurance, by the thawing their regard. What a dome those worse with those. War is as bang with these prints and make zappies,